It's the theorem, and the whole hour will explain this theorem. Okay, so theorem. So there exists a probabilistic algorithm which factorizes a large n-digit number into a polynomial number of steps with polynomial number of steps. I will just write quantum steps, and I will explain what is a quantum step. Okay? So in fact, what Shor claims is that you can get this type of bound, and I will not try to explain really why you can do better than n cube. Okay, the main point is that it is polynomial, and here it has nothing to do with the novelty of the algorithm, namely that it's a quantum algorithm. It's just the fact that you can find some very good algorithm to perform usual multiplication of numbers. That's why those log appears. But if we show that this is something like n3 or n4, it's okay. Okay, so let n be an integer, and this is at most 2n minus 1. N is the n of the n digit, right? So we have a big integer, and the goal is to find a factor. So the Euclidean algorithm find the greatest common divisor of two numbers a, b, which are n-digit number. With n cube steps, you can replace here n cube by this, if you want. This is just because you have to perform n times multiplication. So the step in the algorithm, in the Euclidean algorithm, each time you divide by something, so this is why you get a logarithm in terms of the big N, right? And then you have to multiply in each step or divide. And this is why you get the other n square. So altogether it's n cubed. So it's very good. So it means that if we can at some step apply the Euclidean algorithm, this is good for this problem, right? Okay, so we pick randomly an integer. So this is the first step. So choose randomly an integer between 1 and n. So two possibilities. Either you compute with the Euclidean algorithm, so it's very fast. You don't need a quantum computer. You just use a usual computer to do that. So if it's not 1, then you're done, because you have something which divides n. So it's end of the algorithm. Okay, now suppose it is 1. So in this case, we consider y as an element which is in this group. So this is the cyclic group of order big N, and it's invertible, right? So it's a unit here. So it has an order. So let R is the order of y in this group. Assume we are lucky when we pick y in the sense that the order is an even number. Okay, so if R is even, we can do the following. And okay, by definition, R is the order of y, so it means we get 0. So this shows that n divides the product. Now, we consider a prime factor of n, and the claim is that so at least one of the prime factor of n should divide this. Why? Because otherwise, if no prime factor of n divide this term, then they should all appear here, but then we would have that this is 0 mod n, so it would contradict the definition of the order, right? We would have found a power which is strictly less than R, such that this is 1, okay? So it means that we have the greatest common divisor between n and this is bigger than 1. And now we assume we are even more lucky. So if we are even more lucky, then this is not 0 mod n. Okay, so if it's not 0 mod n, it means that here we got something which is smaller than n. And we again use the Euclidean algorithm, and we find a factor, right? And it's the end if we know what is R. Okay? So if we know what is R,
so if I is not too large, yes, but because if I is large, then this number is too large for applying Euclidean algorithm. If I is of order of n, then this number has about how many?
I mean,
about n large digits, yes.
we'll get log n, right? And of course, we take this, which is mod n. So anyway, it's between 0 and n. We compute mod n, right? Okay. So if we know what is R, we are done. If we are lucky in the sense I said, right? Okay. So if we are not lucky, we try another y and do exactly the same procedure. And again and again. And why does it work? Let me state results, which is elementary, and which relies on the structure of the unit groups of cyclic groups. Okay, of course, if n is even, it's obvious to check, and we divide by 2. So we can assume n is odd, and I denote by m the number of distinct prime factors of n. Then we consider all the cases in which we are lucky, namely, we consider all elements y such that they are prime to n. Okay, such that the order of y is even, and we don't have that. Exactly the two conditions we use. Okay, so this set of number is at least the Euler function of n times 1 minus 1 over 2 power m minus 1. Okay, so it means that if we are not in the case of a prime power, m is at least 2. So half of the case we are okay, right? Because this is the cardinality of this group, right? Okay. So if it's a prime power, it's not a problem. There are techniques to deal the prime powers. So we can assume that there is at least 2 different primes. So conclusion, we need to find R. And that's where we will use this quantum computer. So if you consider this function, so y is fixed. Sorry. So you see that the period of this function is exactly the order of y. And that's one of the main idea of the algorithm. Namely, we will use Fourier transform to detect the period of a periodic function. And finding the period will exactly give us what we need, namely the order of this element. And that's how the algorithm works. Okay, so I need to explain you how you can find a period with a quantum computer. So let me review an easy case.
So maybe the function is x to the y multiplied by x.
No, it's a power. You want to rise to a power, right?
So what is a period as a dynamical system?
No, it's just you multiply y times 1 and take mod n, right? And x is an integer. There is no problem.
Okay, but why do you call it period?
A period, it repeats itself. It's a periodic function, so okay?
Ah, yeah, I see.
Okay, so yeah.
The period is a periodic function, okay.
Okay, so R. Okay? Okay, let me recall what is Fourier transform in the case of the finite cyclic group. So we consider the algebra of the cyclic group of order n. Now n is just an integer. Forget what we fixed about notation before. Okay, it's a Hilbert space. And the isomorphism is here by definition. What is an element of the algebra of the group? Okay, so this is the characteristic function. So this is a canonical identification, and there is a Hilbert product on this finite dimensional complex Hilbert space. And you see, for this scalar product, we get an orthonormal basis. We can consider the characters of the group. So it's easy to check that if you normalize, then you get another orthogonal basis. Right? So we have a Hilbert space, and we have two orthonormal bases. So we defined a transformation which sends the first basis to the second one, or the second one to the first name. So by definition, F, the Fourier transform, send the vector, the unit vector, this one to this vector, okay? And here, by definition, okay, so this is the Fourier transform, and this is then a unitary transformation. Consider the subspace a function of a given period. So assume R is an integer and assume R divides n. Assume it has period R, then certainly we can find one function which has period R. This is So if we take n over R, it has period R. And of course, if we take a power of this, it's also a period. And here, this is the function 1, okay, and we get in this way all the multiple of the quotient here. So we get R of them, and the dimension of this space is R, right? So it proves that they span the set, the subspace of function of period R, right? So the conclusion is that if now we take the Fourier transform of a function of period R, it's a linear combination of those elements, and we know what is the Fourier transform on those elements. So the conclusion is that f of a periodic function of period R, it has some coefficients, and the coefficients which will be non-zero, you see, they will only be multiple of n over R, right? Because here you recover the same index, right? Okay, so please try to remember this fact that we have to consider integer multiple of quotient of the cardinality of the cyclic group by the period R. Because in the algorithm, the goal is to find R. So it will be very useful to have this picture in mind. So a bit is the group with two elements, and it has two states. Which are denoted by 0 and 1. Okay, I will use this notation to define those two states. Okay, now quantum bit is the algebra of the group with two elements. Forget the structure, except that it's a vector space with a chosen bases which we decreed to be orthogonal. Okay, so this is a vector of norm 1. Okay. A quantum state is any superposition such that the norm is 1 of the fundamental states. They are called the fundamental states. N-digit register is the free product of the group with 2 elements, n times. So it has 2 times 2 power n elements. So quantum n-digit register is the Hilbert tensor product n times of 1 qubit. So a state, a quantum state is any superposition this is a A. So this is a complex number. We assume that the norm is 1. And here, so it's a superposition of the fundamental states. A classical computation it's just a map between 2 registers okay, I will call this Vn by definition to save notation. Now, quantum computation is a unitary transformation U from Vn to Vn. So, because it's a unitary transformation, it has an inverse. So the dimension here are, the indices are the same, whether here they are not. So, example of quantum transformation, the Walsh-Hadamard transform so V1, it acts on a single qubit. And it is in the orthogonal basis a reflection of axes with an angle here pi over 8. So a reflection. So it means that the matrix of W1 is this matrix. So you can check that it is a unitary transformation, which is an involution, right? It's a reflection. And by definition, the Walsh-Hadamard transform on Vn is the tensor product of each of the transformation here. So for example, in order to see what W2 is doing, you take the tensor product of the matrix. Okay, so for example, you get this matrix. And what is important for us is to see that if you apply that to the first vector, you see that you have a homogeneous superposition of all states. suppose you have a classical computation and you want to make this computation quantum. So you consider the two indices here and form the tensor product. So that you get the same indices here because it's Vn plus m. And so it goes to x, and here you apply f, and you add y, where here you add things in okay. Okay, so it's mod 2 addition, so it means that again it's an involution. Okay, it's a unitary involution. Okay. Okay, now we can come back to our problem and so n is given. So you choose the unique integer n such that it is between n square when you take the power 2 and 2 times n square. Okay? So you choose this unique n, and you also choose L. Define L to be log 2 of n, and you want an integer, so you take the integer part, the upper integer part, and you form the following register. Okay. I have to explain an identification we will need. So, remember, by definition, this is the tensor product. We can also consider as Hilbert spaces, it's the same as this. And it's also, as a Hilbert space, the same as this. So fundamental states. And here I consider the Beanery expansion Okay, so it's just a trick to write any element of this cyclic group in Beaner, in digit mod 2, right? Okay, and this is isometry so isomorphism of Hilbert space. Those elements are part of orthonormal basis. So we start by applying, and F now. So remember, we have chosen this y at the very beginning, and F is exponentiation. So I represent this element and this, it sits here because I choose L to be okay, so it just creates enough room so that you can embed this. Okay? So this is our function f, which is a classical computation. Now we apply the following transformation. Okay, so the transformation starts with this vector. Okay, so UF and I don't have enough room here. Okay, so I apply this. What do I get? Okay, I just applied the Walsh-Hadamard transform. So it gives me that. Now I apply UF and I have a sum. Okay. And these steps is just the linearity of U, but it is the heart of the algorithm because this can be achieved in polynomial time of n, applying f and applying wn, but what you get is a state where all the values of f appear. Okay, but quantum mechanics prevents you to look at those values. The only thing you can do is do a measurement, and what you get is only one value. Formally, you consider a measurement where here P is an orthogonal projection to the line generated by the fundamental state B. So the probability of observing B is the square of the norm of the state we have. Where you apply the projection. So I apply the projection. So it means here I do nothing, and here I get projection of B onto the fundamental state f of x. So this is the Hilbert norm, and I have to take the square. Now, what is this square? What is this state? Sorry. Okay, so if f of x is equal to b, then we get b, otherwise we get 0. And this is the cardinality of the preimage of B divided by 2n, right? So if we observe B, then the probability of observing B is non-zero, so it means that this set is non-zero, is non-empty. So if we observe B, then this is non-empty, and it means that we can describe this set as A plus K times R, where we have some integer which is smaller than the period, and K is an integer, and Ka is just what you need to stop before you get out of the cyclic group. Okay. So let me check with my notes. Okay. Now, there is another point, is that if we observe B, then after the measurement, we know what is the state. So the state is what the projection is normalized. Okay, so this is the normalization, and this is the state. Okay. Now I want to write this. You see, this is 1 over square root of key A. By definition of key A, you see it describes exactly the cardinality of the preimage. Okay, and here, what do I have? Okay, I have this element, and there is a second component. So now I want to define a function this is 1 over square root of ka if r divides x minus a, and otherwise it's 0. So with this, you can rewrite this part simply like that. So in other words, the function psi is just defined in order to express what we get here in the first register as a function. Now this function, we will apply the Fourier transform to it. So we have the first component here, which is just the function phi a, and we get b. So it's the Fourier transform, okay, f of a times b. Now we apply another measurement. We now measure the first register. So we have the projection PC, okay, where so it's the orthonormal projection onto the line C times C, as before. Okay, so we have these states, and as a result of the measurement, we will get a value C. So we observe the value C with probability okay, so I project, so it picks just this component, so it means that the norm is just the complex norm of the function applied to C, sorry. Okay. Now we can find the period because of the following theorem. So the probability that we observe C such that there exists an integer S with the property that if you divide C by 2 to the n, subtract S over R, then this is smaller than 1 over 2 R squared. So the probability of getting such a value is at least this number. So I have to explain 3 things to finish. The first things I want to explain is why there is a chance that this proposition is true. The proof is elementary. By the way, for people who are interested in having the notes of this talk, I can send copies of the notes. So it's easy to prove, but let me give you a reason why it's not surprising. So you see, I just multiply by 2 to the n here. Okay, so this is the same. So here you recognize what we saw with the Fourier transform of periodic function. Namely, in the special case, the period divides 2n. In fact, there is absolutely no reason that it happens, but the idea is that this is a perturbation of the periodic case. And you see, what we hope is that the coefficient of the Fourier transform, which will appear with high probability, they are multiples of the order of the group divided by the period. And that's what I ask you not to forget when we spoke about periodic function in Fourier transform, right? So in the case of the periodic case, it has to be equal. So it's very natural to expect that this is almost 0. And indeed, there is a choice here which makes this factor at least 1, so it makes sense.
Should it be R squared?
There is an R square, thank you. And the point is that at the very beginning of the algorithm, we choose big N and 2n with some relation, and this is at least 1 because R is smaller than big N, of course, and big N was such that its square, thank you, was smaller than 2n, right? That's why. Okay, so second thing, how does it help? Because we want to find R. And this is because those who knows continued fraction, they know that if you consider this rational number, you can write down with the Euclidean algorithm what is the expansion, right? And the point is that if a rational number is so close to this number, then it has to be a convergent. So it means that if you do the list of the convergent, this guy, it has to be in this list. And now if, oh, I forgot that I also want to say that this is 1, so there is even less element such that this is true because I add some condition. So if you can't make some simplification, then it means that you just have to look at this list and you will find the order, what you want, as a denominator, right? And this can be done with the Euclidean algorithm, so we find R in polynomial time. Okay, so the last thing is why this is not too small, because this is the probability. If it goes to 0, it's bad. Now the point is that here this is the Euler function, and we know, in fact, Chebyshev has some contribution to that. We know that there is a constant. I mean, you can do better than what I write here. There is an explicit constant such that this is log R. Okay? So yes, it goes to 0, but it goes to 0 very, very slowly. So it means you can repeat the steps, and you will win against this probability which goes to 0. So you will get R. Okay, so that's all I wanted to explain, and sorry I'm not really in the time, but thank you very much for your attention.
Well, any questions? Comments?
Can you just explain briefly, re-explain how do you understand what's a measurement?
Yes, by definition, you have a Hilbert space, and you have a family of orthogonal projections such that they together commute if they are different, and such that the sum is the identity. So it's like a partition of the identity. And here it's just a very special case of this more general situation where you choose the coordinates as the measurement. Right. And okay, so that's the definition of a measurement. And then the postulates of quantum mechanics says that if you have a state, you apply a measurement, what you get is just the name of the measurement. Namely, this family is indexed by numbers, like in my case here, this is C in my notation. So the result of a measurement is just the name of one of these projections. So in our case, the names are chosen such that they give us an integer, which is relevant for us. And the second point is that when you apply the measurement, after the measurement, the system is in the state which is just the state you were measuring, where you apply the projection and you normalize. Because the probability of measuring a state is just the square of the norm of the state, right? So because you just know what it is, it has to be of norm 1, so that's why you renormalize.
Any other questions? So let us thank the speaker.
Thank you.